Hello. So our team is composed by Sergio Cordero and me, Emilio Flores, and what we did for this final project is that we tried 4 different approaches. First approach, we tried modifying the OpenCV source code in order to create a random forest and to train them with parallelism to help the time be divided by the amount of threads that you have, so in order to the training process to be much faster. However, because of the way it is made, every time we created a new thread, there will be more granularity than before, and because of that, the amount of execution time, the CPU time, will increase way more than it was without threads. So that's when we discarded this approach. The second approach, is we actually tried to make a random forest with parallelism, but we did around 350 lines of code, and that's when we realized that this was just way too much to be done by a final project of 2 students. And actually this attempt was made by a masters somewhere in the world. The link is in the description. But they did it all together, around 20 people, to make this random forest with parallelism for their thesis of the masters. So that's why we couldn't do it. It was too hard for us. The third approach was we found this Huffman algorithm. The Huffman algorithm is used for encoding and decoding text, and it's found on the internet. But I used one that I had from a previous class in algorithms class, and I modified it first to create Windows threads. As you can see in the left, that's the function that's most crucial. It's a linear search. Well, you cannot see here the operations, but in here there's a linear search, and that's where they try to find a specific value from inside a vector of pairs. If it finds, it returns, else it just continues to the next iteration. The problem is, as you can see on the right, it was just creating way too many threads, and this brings a lot of CPU time, and it's really inefficient. Of course, if I did it differently and I invested way more time for this, probably I would have had the right answer with WinThreads. But however, the fastest ones we were able to come up with was just to use OpenMP, which is as you can see here in the left, this is the function, the normal function. It's one thread, no optimizations, no nothing, and we modified it to the right. We added that line of code. We had to modify a little bit the code, and that created a speed up of around 2.2 x. You will see here are the analysis and statistics that the Intel Parallel Studio brings up when you execute the program. On the right, you have the same program executed without OpenMP, and you get 23 seconds. And on the left, with OpenMP, you get roughly 12 seconds. And of course, there's much that can be done. As you can see here, there's a lot of idle time, and a lot of the computation is done in one thread, but it can get better. But however, for the sake of this project, we just wanted to make it simple to show the contrast from just a single line of code. This one was the most crucial. The second example we did, it took way too much time, the one without the OpenMP, 850 seconds, and the one with OpenMP, it's less than half. As you can see, there's much performance gain from this. And of course, again, if I were to implement it in a better way or a better approach, maybe I could have gotten like a 4x speed up. And here are the references, just if you want to pause and continue. But I will go ahead and show you the live demo. This is a code. It's around 800 lines of code. Much of it is not used for this project. However, I will just go ahead and run first. Let me show you the line that's with Pragma, the OpenMP. Right now it's activated. I will deactivate it and run the same example, but using the Intel analysis tools to show you the speed up. I'm just compiling right now. Then I run this analysis. It should take around 15 seconds, 16, something like that. Right now it's running, and when it finishes, the Intel will do the analysis, and I will go ahead and just uncomment the line that I did comment. Okay, it should be around almost done. Almost. Keep in mind that this is actually decompressing the file. It's the input it takes is a compressed file using the Huffman algorithm, and it decompresses it and gets the original text. It is working, but I'm not going to show it right now. Here, it took 36 seconds, more than I was expecting. So I'm just going to uncomment this and rebuild and then rerun the analysis so you can see the speed up. I'm thinking it's gonna be more than 2x speed up right now, but just go ahead and run it and see what it tells us. Alright, so I think it was around 12. Yep, 11 seconds. This is 3 times the speed up. This is a lot that you can accomplish by just rewriting a little bit your code and writing one pragma directive in the code. As you can see, there's a lot of spin time. Spin time means when the program is waiting, or pretty much in an infinite loop. And that's what happens here. I'm just going to show you right now the code. Once, this is the linear, the search. When it finds what it was looking for, it will activate this flag, and this flag is shared among all of the threads. So whenever it's activated, this condition will never execute anymore. So the threads that were already running will just loop until it finishes the loop. So that's waiting time. So say you have 4 threads, one finds it real fast, the other ones will just have to wait and finish by looping through their given indexes that they were supposed to look for. And this is what brings up the speed time, the spin time up. And there's nothing you can do about it right now. In OpenMP you cannot terminate a thread. You can with win threads, but however, again, I did not do the right approach, but that's maybe for a future improvement. And as you can see here, this is the performance gain you get, 36 seconds, around 11 seconds. And that's about it. Thank you for listening.